In this goal, we're going to look at Graham's law. Graham's law explains the relative rates at which two gases will effuse out at the same temperature. And we need to understand the difference between diffusion and effusion. So look in this lower right-hand corner at these pictures. So diffusion is when two gases just mix. So a good example of this is you're sitting in your history class in the back row, and in through the front door comes this young man, and he is drenched in cologne. So it takes a moment, but eventually you can smell his cologne all throughout the whole room. And you'll keep smelling that until your nose gets fatigued for smelling it all the time, and then you start not smelling it. But right there at first, it's going to be really, really strong. So what's happening is as he walks into that room, that cologne will diffuse all through the air in that room until it is all evenly mixed. So that's diffusion. It goes from a place of high concentration to low concentration until everything's mixed. Let's look at effusion. So in effusion, we take our gas sample and in one side of our container here, and then the other side we have a vacuum. And then we poke a pinhole through and we see how fast the gas travels through that little hole into that vacuum. So it's a way to measure the rate of how fast something will travel, this effusion. And what we find is the smaller gases, they travel faster. The smaller the mass travels faster. So we have a formula right here. This is Graham's law of effusion. And you're not exactly figuring out the rate or how fast these are. You're just comparing your first gas and your second gas, or gas A and gas B. Now notice how it's set up. So I have rate of A divided by rate of B, and then on the other side I have the square root of the molar mass of B divided by the molar mass of A. So notice that when you're looking at the rate of A compared to the rate of B, when you go to do the square root, you should have your big number on top. So you want to have the smaller gas be gas A. We already know it travels faster. Graham's law just tells us how fast. Or how much faster is what Graham's law tells us. So let's do a Graham's law problem here. So it says find the relative rate of effusion for krypton. And so looking at the periodic table, I find that the mass of krypton is 83.8, and it's Kr. And then bromine. Bromine is Br2. And so looking at the molar mass of bromine, it is 80. So 80 plus 80, the molar mass of bromine is 160. So let's set up our problem. So we have the rate of our small gas, so that would be the krypton, compared to the rate of our larger gas. And it's equal to the square root of the larger gas on top now, 160 over 83.8. And when I put this in my calculator and take the square root, I get 1.38 is my answer. So what does this mean? This means that we already know that krypton goes faster than bromine because it's smaller in mass. So this tells us that krypton is 1.38 times faster than bromine. So let's look at this thought problem. So if I combine hydrochloric acid, which is a gas in this case, and ammonia gas, I actually get a solid precipitate. So it's basically a white cloud that forms and then will settle. And if I put it a little sample on either end of this straw, and if I put each sample into the straw at the same time, where is that precipitate going to form? Is it going to form right in the middle? Is it going to form closer to the ammonia? Is it going to form closer to the hydrochloric acid? Well, let's find the molar masses of each of our substances to find out which one is the smaller gas. So let's start off with the HCl. So I have 1 plus 35.5, and that would be 36.5. And then over here I have 14 plus 3 times 1, 17 grams is the molar mass. So which gas is going to travel faster? Well, you're right. It's the ammonia is going to travel faster. So when put into the straw at the same time, the ammonia will race down and catch the HCl right here. Okay. So the ammonia is about half as much as the hydrochloric acid gas. So this is just showing the speed of the ammonia in comparison to the HCl. And we can calculate Graham's law for this. So we'll do the rate of the ammonia divided by the rate of the HCl. And then we have the square root of 36.5 divided by 17. And when I get the square root, I get for my answer 1.5 times faster. So we see that ammonia is 1.5 times faster than that HCl.